In Manchester, New Hampshire in 1891, a flywheel failed at the Amoskeag Manufacturing Company. It weighed 56 tons. Cast iron shatters without warning, and each section continues in the direction it was already going. Iron punched through the engine house walls. 3 workers did not make it out. The same weight flywheel had stood at the 1876 Philadelphia World's Fair, with 10 million Americans walking past it, no barrier between them and the rim, and nobody warned them what they were standing next to. But that is the story of the Corliss engine, and it starts 15 years before Manchester. If you are new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country and the things those things cost. Subscribe and leave a comment with the next story you want us to dig into. To understand the Corliss engine, you have to understand the world it was built for. In the 1870s, there were no individual electric motors attached to machines on factory floors. Power did not arrive at each workstation independently. It arrived once, at one point, and traveled from that point to every machine in the building through a system that was ingenious, efficient, and laced with risk in ways the men who worked inside it understood very well. A large central steam engine sat in an engine room at one end of the facility. Its power traveled across the entire factory floor through overhead rotating steel shafts running the length of the building. Off those shafts, hundreds of leather belts dropped down to every individual machine below. Every loom, every lathe, every press and pump and cutting tool on the floor, all of them running off the same source. When the central engine ran, everything ran. When it stopped, the entire building went dark. Those leather belts were moving at the speed of a galloping horse. Workers who maintain the overhead shafts walk through spaces where a belt 15 inches wide moved at head height, and a belt catching a loose sleeve did not give you time to react. A belt snapping under tension crossed the room before anyone could call a warning. But the belts were the visible danger. The thing most workers in those buildings stopped seeing as a threat was at the center of the whole system. At the heart of every central steam engine was a flywheel. A massive cast iron wheel mounted on the main crankshaft, spinning continuously throughout every shift. Its job was to smooth the power delivery from the engine. Steam pistons fire in pulses, each stroke surging then falling, and in a textile mill running dozens of looms, that uneven motion snapped threads and ruined product. The flywheel absorbed each pulse and released energy between strokes, keeping the motion smooth and the floor running at consistent speed. The heavier the flywheel and the wider its diameter, the more energy it stored in the rotating rim. And the relationship between speed and stored energy was not a straight line. Stored kinetic energy in a rotating wheel grows with the square of its angular velocity. A flywheel running 10% above its rated speed was not storing 10% more energy. It was storing roughly 21% more, at 20% above rated speed. The rim was holding roughly 44% more energy than the engineers had calculated for. That mathematics had a specific meaning in practice, and the men who ran those engine rooms understood it. More speed meant more energy. More energy meant the iron holding it had to hold more than it was designed to hold. Cast iron has a property that steel does not. Steel bends and deforms under increasing stress, stretching and giving visible warning before the point of failure. Cast iron holds its shape all the way up to its tensile limit, and at that point, it does not crack gradually. It shatters all at once, without warning, without a preceding noise the floor crew could report hearing, without a wobble or vibration that reached the men working nearby. Engineers who investigated flywheel failures in American and British mills during the 1880s and the 1890s documented what that meant in practice. Iron sections weighing several hundred pounds were found embedded in the ground outside factory buildings. Fragments had punched through brick walls 2 and 3 feet thick. Debris was recovered more than the length of a football field from the original engine room. The failures came without visible warning on ordinary shifts. Beside machines the workers had been running for years without incident. By 1876, American factories had been running on this central engine system for decades, and the machines had been growing larger with every passing year. Mills in Lowell and Patterson in the steelworks of Pittsburgh had central flywheels weighing 20, 30, 50 tons. The risk grew with the wheel. Nobody stopped the growth because the larger the flywheel, the more stable the floor output, and more stable floor output meant more product per shift. That is the world George Henry Corliss was working inside when the organizers of the 1876 Centennial Exhibition came to him. Corliss ran a manufacturing operation in Providence, Rhode Island, and by the mid-1870s he had a reputation that few American engineers could match. His name was attached to a specific steam valve design that controlled how steam entered and exhausted from the cylinder more efficiently than anything else available at the time. Corliss engines had been running in New England textile mills, in Pennsylvania, steelworks, and in factories across the industrial Northeast for years. Factory owners specified them because they ran reliably and kept running. What the exhibition committee asked him to build was something he had never attempted, and no one else had attempted either. A single engine capable of delivering power to every machine and machinery hall simultaneously, running reliably for 6 months, in front of an international audience that included heads of state, engineers from every major industrial nation, and journalists from every major publication in the world. Corliss agreed to build it at his own expense. His one condition was that the exhibition committee return the machine to him when the fair ended. He was not doing this for a contract payment. He was doing it because it was the most ambitious steam engine anyone had ever attempted, and he intended to be the one who built it. The engine was assembled at his Providence works over 2 years. 2 vertical steam cylinders, each with a 44-inch bore, drove a single crankshaft mounted at the top of the central structure, 56 feet above the floor. That crankshaft connected directly to the flywheel. The flywheel was 30 feet across and weighed 56 tons. Because no foundry in America could cast a wheel that size in a single pour, it was built in sections and bolted together at the rim. Each bolted joint was a point where rotational stress would concentrate in ways the engineering of that era could not fully calculate and had no reliable method to inspect. The total assembled weight of the engine was 700 tons. Every pound of it had to be transported from Providence to Philadelphia, reassembled inside Machinery Hall, and trusted to run without failure for 6 months. At operating speed, the rim of that flywheel traveled at 66 feet per second. That is roughly 45 miles per hour, not the center of the wheel. The outer edge of a 56-ton casting in bolted sections, spinning inside an open exhibition hall. The nearest visitor walkway inside Machinery Hall placed the public within 30 feet of that rim. The building's walls were stone and brick, designed to hold weight and keep out weather. They were not designed to stop sections of cast iron traveling at highway speed. On May 10, 1876, President Ulysses Grant and Emperor Dom Pedro II of Brazil stood at the starting levers of the Corliss engine in front of 100,000 people. They moved the levers together. Steam entered the cylinders, the crankshaft turned, and the flywheel began to rotate. Power moved through the main shaft the length of Machinery Hall and out through hundreds of leather belts to every machine on the floor. Witnesses described the sound as a rising mechanical wind filling the building from one end to the other. The floor vibrated. Workers at the printing presses began feeding paper immediately, and freshly printed newspapers were handed to visitors within minutes. Dom Pedro stood from his chair and said the machine was astonishing. He had supervised major industrial operations in South America and toured the best factories in Europe. He had never seen anything like it. Could you imagine walking into that building in 1876? A machine the height of a 6-story building, 1.7 million pounds of assembled iron, running every piece of machinery in 14 acres simultaneously. In June of 1876, about a month after opening day, something else happened inside that building. Alexander Graham Bell set up his electrical apparatus in the exhibition's scientific section and ran a wire to a receiver at the far end of the room. Dom Pedro, who had returned specifically after hearing reports of the new device, held the receiver to his ear. Bell spoke from the transmitter at the far end of the wire, and Dom Pedro stood from his chair and said, out loud, that the thing talked. That demonstration became the moment the telephone entered American public consciousness. Every major newspaper in the country reprinted the story within days. But all of it happened inside the same building, under the same roof, powered by the same flywheel that was spinning 30 feet from the visitor's walkway. The most significant communication technology in modern history made its public debut inside a machine that could have leveled the building if the governor had stuck on the wrong afternoon. 10 million Americans came to that exhibition over 6 months, roughly 1 in 5 people alive in the country at that time. They walked through Machinery Hall, they watched the flywheel turn, they picked up the newspapers the printing presses produced, and they went home to every corner of the country carrying a specific image. The future of American industry looked like controlled, majestic, orderly mechanical power. A machine so large it was almost calm in its motion, its immense scale making the danger invisible precisely because everything looked so steady and controlled. The technology had arrived, and it was clearly in charge of itself. But what those visitors were standing next to was something the calm appearance concealed entirely. The flywheel spinning in front of them had no enclosure, no housing around the rim, and no barrier between 56 tons of moving cast iron and the visitor walkways. The bolted section construction meant the rim was held together at its joints by fasteners that experienced the full rotational stress of a 30-foot wheel at operating speed on every rotation for every one of the 173 operating days the exhibition ran. Nobody standing in Machinery Hall that season had any way of knowing whether the iron in those sections was sound, or whether it contained the kind of internal void or inclusion that would concentrate stress until the material reached its limit. There was no inspection standard that would have told them. The technology to find such defects did not exist. Corliss had inspected every casting himself and was confident in the iron. That confidence was earned because the machine ran the full 6 months without failure. But there is a specific and important difference between a machine that ran without failure and a machine that could not have failed. The Corliss engine was the first. The second is a different category, and nothing about the physics of cast iron or the inspection methods of 1876 placed it there. The thing controlling whether the flywheel held together was not only the quality of the iron, it was also a small mechanical device mounted above the crankshaft called a centrifugal governor. The centrifugal governor is one of the most elegant mechanisms in the history of mechanical engineering. 2 weighted balls hang on jointed arms from a vertical rotating spindle connected to the engine's output shaft. As the engine speeds up, the balls swing outward from centrifugal force. As they swing outward, the arms they are mounted on pull on a collar that throttles back the steam valve. Speed goes up, steam goes down, engine slows to rated speed. Speed goes down, steam comes up, engine accelerates back. The governor's the machine's self-correcting system, the mechanism that keeps a steam engine running at its intended speed despite varying loads. If you are finding this story as important as anything we have covered on this channel, go ahead and hit subscribe right now and leave a comment below with the next machine you want to see. When the governor worked correctly, the Corliss engine was one of the most stable power sources American industry had ever seen. This was a large part of why Corliss engines had the reputation they did. The valve timing and the governor together kept output remarkably consistent under changing loads, which was what factory owners needed to run precise machinery. But the governor was also the single point of failure that could turn a stable machine into a runaway. If the governor seized, or if the linkage between the governor arms and the steam throttle stuck, or if the governor balls fouled and stopped responding to speed changes, the engine had no self-correction. Steam continued entering the cylinders at whatever rate the last throttle position allowed, and the engine began to accelerate. The flywheel accelerated with it. As the flywheel sped up, the stored energy in the rim rose with the square of the speed. The iron in the rim experienced more stress with every rotation, and nobody on the floor watching the machine had any reliable way to know how far above rated speed the engine had climbed, or how close the rim was to the stress level at which cast iron stops holding and starts throwing. The experienced engine tender knew what a governor failure looked like in its early stages. A slight increase in the machine rhythm, a change in the floor vibration, a pitch shift in the hum the machine produced at operating speed. The problem was the gap between noticing and intervening. The governor linkage that had seized had to be reached and physically freed while the machine was running, in an engine room where the flywheel was already above rated speed and climbing. The men who ran those systems understood, in a practical way, that the window between the moment you recognized an overspeed event and the moment the rim reached its limit was not always long enough. They still went back to the engine room the next shift, because the alternative to going back was not getting paid, and not getting paid had its own consequences in a mill town. Mill engineers of the period documented overspeed events in technical journals. The pattern was consistent. The men who ran the engine would notice the speed increase and attempt to intervene at the governor or at the steam supply. When the intervention succeeded in time, the machine came back to rated speed and nothing happened. When the intervention did not succeed in time, the outcome was the Amaskiag result. 3 workers were killed, iron sections punched through the engine room walls, and debris was scattered across multiple buildings. When investigators reached the engine room afterward and looked at the governor, they found exactly what the men who had not made it out had probably seen in the last moments of the shift. A mechanism that had stopped doing its job while the machine it was supposed to control kept accelerating toward a limit the iron could not hold. Now here is what the Amaskiag disaster actually means when you set it against the Centennial exhibition. The Amaskiag flywheel that failed in 1891 weighed 56 tons, the same weight as the flywheel that Grant and Dom Pedro had started in Philadelphia in 1876. The same material, the same era, the same bolted section cast iron construction, the same design logic. The difference between the machine that ran for 6 months in front of 10 million visitors and the machine that killed 3 men in Manchester was not better engineering or a superior understanding of flywheel physics. It was which foundry had poured the iron, what the internal condition of each casting happened to be on the day it entered service, and whether the invisible flaws in that particular pour happened to fall within the limits the iron could hold under continuous rotation. The people at the Amaskiag Works in 1891 who did not come home from their shift were doing the same job, under the same conditions, beside the same class of machine that workers in Machinery Hall had done every day for 6 months in 1876. But the workers in Machinery Hall were part of the exhibition. The workers at Amaskiag were part of the production floor. The distinction matters because one group was visible, recorded in accounts of the fair and present in newspaper illustrations of the opening ceremony, and the other group was not visible in any record that has survived their shift. The distinction between a famous machine that became a symbol of American progress and a machine that killed 3 men on an ordinary shift in New Hampshire was not a difference in engineering. It was a difference in luck. And in an era before materials testing and X-ray inspection, there was no reliable way to know which side of that line your particular machine was on until the machine told you. The exhibition closed in November of 1876. Corliss had the engine disassembled and the components shipped to Chicago, where it was sold to the Pullman Palace Car Company, the manufacturer of the sleeping railroad cars that made long-distance travel comfortable for Americans who could afford the fare. The engine was reassembled at the Pullman Works on the south side of Chicago. The flywheel that President Grant had started in front of 100,000 people now turned inside a production facility, driving the machinery that built railroad cars, with no ceremony marking its transfer and no newspaper noting its arrival. The most famous machine in America in 1876 was running ordinary production shifts in a Chicago factory by 1878, and had been entirely forgotten by the public within a decade. It ran at the Pullman Works for years, alongside workers who likely had no idea they were operating beside the centerpiece of the great American public event of the 19th century. But in the first decade of the 20th century, individual electric motors began replacing central steam plants across American manufacturing. Smaller distributed motors were cheaper to run, simpler to maintain, and when one failed, one machine stopped rather than an entire building losing power. A cotton mill or a steel works running on a central Corliss engine was as dependent on that one machine as it had ever been on the original 1870s installations. One governor failure, one bearing failure, one crankshaft problem, and the entire floor went dark. Individual electric motors on each machine eliminated that single point of failure at the cost of a more complex installation. Factory owners calculated the numbers, and the numbers said electric motors. The single point of failure was gone. The Corliss engine was removed from service sometime in the early 20th century and scrapped for the iron. The 700-ton machine that Grant had started, that had powered Bell's first public telephone demonstration, that had run as the centerpiece of the greatest public gathering in American history to that point, was reduced to iron without a newspaper account of its final day, without public ceremony, and without a recorded date that anyone has been able to locate since. Machinery Hall itself had already burned in 1876, destroyed by a fire shortly after the fair closed. The grounds were absorbed back into Fairmount Park. The stone foundation that had anchored 700 tons of engine was eventually covered with grass. What stays is what those men understood, that nobody in Machinery Hall was told. The steam engine tenders, the flywheel mechanics, the millwrights who kept those central drive plants turning, none of them watched that flywheel spin and saw what the visitors saw. They did not see a majestic demonstration of American progress. They saw a machine they were responsible for keeping inside its limits, and they knew exactly what was stored in the rim if they failed to do that. Those men were the best paid workers in their plants, and every person in the plant understood the reason for the premium. The job paid more because the job was the most likely to kill you, and that calculation was understood by everyone, including the men who accepted it, because the alternative to accepting it was not getting paid, and not getting paid had its own consequences in a mill town in 1880. Most of the workers who stood beside those flywheels for 12-hour shifts, 6 days a week, in the mills of Lowell and Patterson and Manchester and Pittsburgh left no recoverable name in any record. The ones who were killed in flywheel failures appear in engineering journals as aggregate statistics. Fatal accidents per year of operation, injuries per 1,000 workers. The men behind those numbers do not have names anyone can find in any searchable database, because the industrial era recorded production output and aggregate failure rates, not the individuals who made the output and paid the failure rates. The Corliss engine was lucky and famous because it was lucky, and forgotten because once the luck was established and the fair was over, it became just a machine running a shift in a Chicago factory. The men who tended engines exactly like it, in mills that did not get lucky, are gone from the record entirely. That is not an accident of how the era documented itself. It is a deliberate feature of how the industrial record was kept, because the people keeping it had no incentive to record what they were not required to count. The danger was inside the iron from the day it was poured, controlled by a governor that could fail, producing a rim speed nobody standing near it fully reckoned with. The men who worked beside it knew. The 10 million visitors in Philadelphia did not. The 3 workers in Manchester in 1891 had the same exposure and a different outcome. The governor failed, the iron failed, and the maintenance record noted a replacement. The Corliss engine ran for 173 days in front of 10 million people, and nobody asked what would happen if it broke. The men who tended those machines on the night shift in the mills of Lowell, Pittsburgh, and Manchester asked that question every day. If you want to keep following those stories, subscribe to Steel and Sweat.